Hi, everyone. Thank you so much for having me here. I'm absolutely delighted to be here. I'm going to spend a few minutes talking to you about static typing. It's a big subject, and I can only really sketch it here. So I've written up a more detailed version of this talk on my blog. If anything I say sounds interesting, you can find out more at that URL. It'll be on the last slide as well. In November, I was at RubyConf in San Diego, where Matz used his opening keynote to talk about what might come next for Ruby. In particular, he said that Ruby 3.0 may happen in the next 10 years, and that it might see some new concurrency features, just-in-time compiler, perhaps the LLVM JIT, and static typing. That's right, static typing. A lot of people were worried when they heard that, and that's understandable because in the Ruby community we don't get much direct exposure to static type systems, and they immediately make us think of languages like C and Java. So I want to unpack Matz's remarks a little bit and provide a bit of context and vocabulary around them in the hope of encouraging a productive conversation about static typing in Ruby. To cut to the chase, my interpretation is that Matz was proposing three specific ideas beyond just Ruby should have static typing, and those ideas are structural typing, implicit typing, and soft typing. And those ideas provide an important degree of subtlety beyond the words static typing that would steer the language towards something very different from just Ruby that feels like Java. So if you already know what those words mean, I don't have anything to tell you, but if they're new to you, I'd like to convince you that they represent interesting ideas that go beyond the features of the static type systems you might have used in the past. So maybe they're interesting to think about in the context of Ruby. I mean, maybe not, maybe they're worthless, but let's be specific about what we're considering first. As a way to get you into this subject, I'd like you to think about how computers handle values. Imagine you could crack open your laptop or your smartphone and zoom into the microscopic level and look deep into its memory to see what was stored there. You'd see something like this, an undifferentiated soup of ones and zeros, binary data. And what do those patterns of ones and zeros mean? Well, you can't tell just by looking at them. They don't have any inherent meaning, at least not an interesting one. So at the lowest level, every value inside a computer looks the same, just this pattern of ones and zeros. But when we write code to manipulate a value, we usually have a specific interpretation in mind. A given pattern of ones and zeros being used by our program might represent an unsigned or signed integer, or a floating point number, or a letter of the alphabet, or the integer address of a memory location where we can find some data structure, and so on. Now, the primitive operations inside a computer generally just assume that the values they're given are supposed to be interpreted in a particular way. For example, at some level, a computer will have different operations for add to integers and add to floating point numbers, because every pattern of bits has a different meaning depending on whether it's being interpreted as an integer or a floating point number. If we add these two 32-bit patterns of ones and zeros by interpreting them as unsigned integers, we get this result. If we add the same patterns of ones and zeros by interpreting them as floating point numbers, we get a different result. And of course, if those bits represent something that's not an absolute quantity, like a memory address or a timestamp, it might not make sense to add them at all. This points to a fundamental problem in constructing computer programs. How do we, as programmers, avoid values being accidentally misinterpreted? If we store in memory some data that represents an unsigned integer, and then later on we retrieve that data and accidentally use it as though it represents a floating point number or a pointer, the result of our program is going to be junk. And the machine code that actually gets executed by CPUs doesn't get involved in this issue at all. In this ARM assembly code, each register just contains an interpretation-agnostic pattern of bits called a word, and these instructions treat the register first as an integer, the register R1, as an integer, then as the address of an integer, then the address of a floating point number, and then as an offset of some other address, and then as the target address of a branch, and it's all the same word that's being treated in all those different ways. This programming language is called BCPL. It's a direct ancestor of C, and it's ultimately a kind of portable assembly language. Each value is a word of bits, and those bits get interpreted differently depending on which operator you use them with. In this factorial program, the variables I and n are populated with words representing integers, and they happen to be consistently used as arguments to integer multiplication and subtraction operations, which treat their contents as integers, so everything works fine. But in the same program, we could just as well add I and n together while treating them as floating point numbers with this hash plus floating point addition operator to get a nonsense result. Or we could multiply n by a floating point number with the hash star multiplication operator, again, giving nonsense because n's contents represent an integer. Or we could even treat n as a pointer, interpreting its contents as an address to read from or write to, which would almost certainly be a disaster. Even these two floating point literals are being incorrectly multiplied with the integer multiplication operation to give a junk answer. Assembly and BCPL rely completely on the programmer to keep their own mental model of which values should be interpreted in which ways, and to make sure that every use of an operation is appropriate for the values it's being applied to. Which brings us to type systems. Type systems are a programming language technology designed to prevent this kind of error. The idea is that by incorporating a type system into a programming language, you can reduce or perhaps eliminate completely the ability of the programmer to accidentally write code that misinterprets a value. Broadly speaking, a type system is a set of rules that expect some of the things in our program to have pieces of metadata attached to them. And I'm being intentionally vague there because the exact meaning of thing and the exact content of the metadata depends on the particular type system. But regardless of the details, those pieces of metadata are called types, and they contain information about the intended interpretation of the thing they're attached to. The rules of a type system describe how to check this metadata to prevent errors caused by misinterpretation. So the general idea is to take the implicit information about value representation out of the mind of the programmer and put it into the computer as explicit metadata, make it part of the program somehow, so that it can be systematically checked for consistency with the operations used on those values. The design of type systems can get very complicated, but there are three big obvious questions to answer. Firstly, where does the metadata go? What are the things in your program that it gets attached to? Secondly, what does the metadata look like? What information does a type tell us about how to interpret a value? And finally, where does that metadata come from? Who decides how values should be interpreted? I'll start with the first question. Where does the metadata go? Well, there are three main answers to that we see in the wild. The simplest possible answer is that the metadata goes nowhere. We don't have any metadata at all. That's the case for assembly language and BCPL. Programming languages that do this are usually called untyped languages. A certain kind of person calls them unityped languages because they take the sardonic perspective that everything in the program has been annotated with the same single piece of metadata, and aha, you fool, I tricked you, it's the empty piece of metadata. But that's a bit like saying that everyone at RubyConf Australia is riding a horse, it's just that we all happen to be riding the null horse. It might be mathematically accurate, but it's not very enlightening, and, you know, I don't see any horses here, so why are you bringing horses into it in the first place? How did you even get in here? Another popular answer is that the metadata goes on values. That means that our actual in-memory representation of values includes extra information about how they should be interpreted. And once we have a convention about how to read that information, the programming language's operations can check it to make sure they've been given compatible arguments. This is how Ruby works. Inside the C implementation of the official Ruby interpreter, MRI, there's a data structure called RBasic that contains a load of flags. And those flags contain information about whether a value is a string, a regular expression, an array, an instance of a user-defined class, and so on. Every Ruby object begins with an RBasic structure that contains these flags. MRI defines some macros and helper functions that are able to extract these flags from any Ruby value. So when the runtime wants to do some operation on a value, it can look at the type of the value and raise an exception if it's not what it expected. And then the program can exit gracefully instead of giving a junk result. Programming languages that do this are called dynamically typed, and we say dynamic because you don't see types just by looking at the program. They appear on the fly in memory when the program is run. And the third popular answer to where does the metadata go is on pieces of source code. Rather than store metadata on values in memory when the program is running, we put it on the actual text of the program as part of the syntax of expressions and statements. This is how a language like C works. In the source of a C program, we can write things like int and long and void to declare the types of variables and functions. The rules of the type system allow all the syntactic occurrences of variables and functions to be checked to make sure the metadata from their declaration matches the way they're being used. If you get this wrong, your program won't even compile. These are called statically typed programming languages. You don't need to run a statically typed program to check its metadata because it's all written right there in the source code. So those are the three main ways of answering the question. There is no metadata, or there is metadata on values, or there's metadata on pieces of source code. And there's a sort of spectrum of increasing safety here. If your program interprets a value wrongly, a static type system can tell you about your mistake at compile time before you ever run the program. A dynamic type system can tell you at the exact moment of misinterpretation during the actual execution of the program, and an untyped language will never tell you. It will just silently produce garbage. All else being equal, safer is better. Of course, all else isn't equal, and you can read my blog post if you want to hear more about that. The second big question was, what does the metadata look like? And this question is independent of whether the types are static or dynamic. It's about deciding what kind of information we want to record about how to interpret values, regardless of where we record it. Most type systems you've seen are probably nominal type systems. That means the types are just names. Like in the C example, which uses names like int and long and void to identify the types. And this is by far the most common kind of metadata. It's what you're used to seeing in C and in Java and virtually all mainstream programming languages. But there's an alternative answer, which is that instead of types being simple names, they can be structures. And implicit in that idea is that you can compare types by comparing their structures and deciding whether they're compatible, rather than just checking whether or not two names are exactly the same. And that arrangement is called a structural type system. Here's an example of what I mean, taken from the Go programming language. Go lets you declare an interface called shape and say that a shape is anything with a method called area that returns a float. And this is the structure I'm talking about. Although the shape interface does have a name for convenience, it's not the name that's important, it's the structure that it refers to. And the structure in question here is just a list of method signatures. Once you have this interface, you can invent new types that conform to it. Here are types called rectangle and circle that both have implementations of an area method. And neither of them explicitly mention the shape interface, but they have a matching structure. And that means we can use rectangle and circle values wherever a shape is expected. We don't have to declare explicit inheritance like in a nominally typed language. We can just use a rectangle or a circle wherever a shape is expected because the structure of rectangle and circle is compatible with the structure of shape. This might remind you a little bit of duck typing. Last big question, where does the metadata come from? This one only really applies in the context of statically typed languages where information has to get attached to pieces of source code somehow. The most obvious answer is that the programmer provides this information by explicitly annotating the source code. After all, the whole point is to capture knowledge from their brain. Going back to that C factorial example, to get this code to compile, we have to actually peck out the strings long and int at every variable and function declaration when we write the program, or if we're lucky, we get our editor or our IDE to do it for us. This is called manifest typing, and the majority of mainstream statically typed languages work like this. They expect the programmer to do all or most of the busy work of annotating the program. The alternative is to let the computer, which usually means the compiler, add the type annotations itself. Every time the programmer uses a particular operation, say adding integers, they're leaking a piece of information about what kind of values, for example integers, they're expecting to see at that particular point in their code. Now, for some languages, it's possible to use a type inference algorithm to move this partial information around, join it together, fill in all the gaps, and eventually reconstruct complete type annotations for every expression in the program, sometimes without needing the programmer to label anything at all. This is a factorial program written in Haskell's interactive console. It looks more like a dynamically typed program than a statically typed one. It's not very different from what we'd write in Ruby or JavaScript, but it's just as statically typed as the C version because Haskell can infer all the type annotations just by looking at how we've used the built-in operations and literals. So the type of everything is completely known before the code ever gets executed. If we ask Haskell what the type of factorial is, it tells us that it's a function which takes any numeric argument that supports equality comparisons. Using type inference to reconstruct source code metadata like this instead of requiring explicit annotations is sometimes called implicit typing. Okay, well, the point of this talk was to unpack what Matz said, but it's almost over and I haven't even mentioned what he said yet. Let's have a quick look at his slides and try to work out what he thinks Ruby 3.0 is going to look like. He does help us out by showing some speculative example code on this slide. He sets the variable a equal to 1 and comments that the type of a is integer. Here's another example he gave. He defines a method called foo that requires x to have a method called toInt. And then he shows two uses of foo, one of which is OK because the object passed in has a toInt method, and the other of which is not OK. On a third slide, he says, a type is represented by a set of methods, and he notes that you could use a class name as a sort of shorthand for that. Now, taken together, I think those slides make it pretty clear where Matz is going with this. Firstly, it's obvious that he's talking about Ruby's type system being static, not just dynamic. Metadata on pieces of source code, not just on runtime values. He just came out and said it during his keynote. But he's also clearly talking about using structural types, not just nominal ones. Those slides say that the metadata should talk about what messages a value responds to, not simply what class it's an instance of. And that's important because it would preserve some of the feel of duck typing. The type of a method argument can specify that it needs to respond to certain messages, and then it will accept any object whose type says it responds to those. And the code he showed didn't have any annotations, which suggests to me that Matz wants an implicit type system that uses type inference to generate as much of the static metadata as possible, instead of making programmers type it in explicitly. The big question is, how would this implicit, structural, static type system actually work? Making all that stuff work for Ruby is a difficult job. For example, integrating structural typing with Ruby's open classes is hard, because if new methods can be added to the string class at any time while the program is running, how do you know what set of method signatures to put in the string type? Matz made a couple of references to a paper from 1991 called Soft Typing, which describes a sort of best of both worlds type system that works by transforming a program at compile time. A type inference algorithm tries to reconstruct static types for the whole program, and in the parts where it fails to do that, it forces those parts to become statically typed by inserting dynamic checks into them. And that turns a situation like these two values may or may not be numbers into you can safely proceed on the assumption that these two values are numbers because an exception will be raised at runtime if they're not. Now that sounds appealing, but reading the paper made me skeptical of how its ideas could be applied to Ruby for a few reasons. Firstly, the soft type system is defined for what they call an idealized functional language, namely a very simple toy language that doesn't exhibit any of Ruby's interesting features. It doesn't even have objects, for example. Secondly, while it does have a clever type inference algorithm, the soft type system doesn't look structural to me. So it doesn't seem like it helps with that particular design goal. And finally, it doesn't actually provide any safety. The goal of soft typing is to make dynamic programs faster by eliminating runtime checks. Instead of having a fully dynamic program, parts of it can be made statically typed so that only the remaining parts need to be checked when it runs. But Matz said that we don't need static typing for speed. He mentioned how successful the V8 and LuaJIT projects have been at making dynamic languages run fast. And that leaves me confused about what benefits soft typing would bring to Ruby. So what's the next step? What should the Ruby community do to start making progress on this whole static typing thing? We have a big challenge ahead of us. Can we bring the safety, performance, and documentation benefits of static typing to Ruby without compromising its flexibility, its friendliness, its humanity? My technical opinion is that we can do it, and my non-technical opinion is that we should do it if we want Ruby to remain competitive and relevant in the next decade. Almost all new languages have some kind of static type system. Rust is a good example of a recent language that's not only statically typed, but which also pushes the boundaries of mainstream type systems by including an ownership system for statically tracking which part of the program is responsible for each allocated region of memory. Facebook released Flow just over a year ago, which is turning out to be a very capable static type checker for JavaScript. Even Perl 6 has optional support for static types, for God's sake. There's no point in Ruby being fashionable just for the sake of fashion, but these new languages are servicing a genuine and growing demand for computers to understand our programs better so they can help us to get them right and make them fast. Safety and software quality is the most important reason why we should be considering this. Imagine being able to catch a broken view helper the first time your Rails application boots on the CI server, instead of when someone hits an obscure page on the admin interface 2 weeks after it's been deployed to production. Now, writing tests is great, but a static type system is like a built-in test suite that catches all the ridiculous, pointless problems you waste time on every day so that you can focus on the interesting ones. We have no reason to fear types. Ruby already has them. They already get checked. The only question is when they should be checked, and the earlier we can check them, the more likely it is that we'll be able to catch silly mistakes before they make it into production. And that's a good thing as long as we can come up with a static type system that understands the kind of programs we want to be able to write in Ruby. These are hard problems, though. Designing a static type system that captures enough safety to be useful while preserving enough flexibility to still feel like Ruby is a serious formal challenge. The soft typing paper doesn't provide the answers for a language like Ruby. I don't know of anything we can take off the shelf here. Most of the pieces exist, but to fit them all together with Ruby requires attention to mathematical detail, as well as a sensitivity to Ruby's aesthetic qualities. It's going to take serious research, not brute force hacking. The answer is probably going to look more like a PhD thesis than a pull request. But there's no reason to be defeatist. There are plenty of smart and motivated people in the Ruby community. There are plenty of interested companies that have the money to pay research staff or to fund a PhD studentship. There is plenty of desire to keep Ruby moving forward and make it a viable and relevant language for the next decade. I hope what I've said today can help to get those conversations started. Thanks very much.